Today we're going to talk about limiting reagents and percent yield. For our examples for today, we're going to use the same chemical equation that we talked about in our previous lecture. With this equation, you have 1 mole of calcium hydroxide reacting with 2 moles of nitric acid to produce 1 mole of calcium nitrate and 2 moles of water. So whenever you're reacting this, previously, I would always start you out with some mass or some number of moles of the reactants and ask you to figure out how many moles of the product were produced. But the thing that was the key to every single one of those reactions was I always said excess of the other reactant. So if I said you start out with 5 moles of calcium hydroxide, I would then proceed to say it reacts with excess nitric acid. So by saying it like that, I made it so you didn't have to worry about what we're going to have to worry about today, and that is the idea of a limiting reagent. So if I were to ask you the question, if you have 1 mole of calcium hydroxide and 2 moles of nitric acid, how many moles of product are produced? It's pretty obvious. You have 1 mole of calcium hydroxide and 2 moles of nitric acid, so you're producing 1 mole of calcium nitrate and 2 moles of water. But let's say I ask you if you have 2 moles of calcium hydroxide and 2 moles of nitric acid. Now how much are you going to produce? Are you going to produce 2 moles of water or 4 moles of water? Are you going to produce 2 moles of calcium nitrate, 1 mole of calcium nitrate, 7, 8, 9? How many are you going to produce? Because the thing here is if you start out with 2 moles of calcium hydroxide, that doesn't change your coefficient. You just simply have 2 moles present. You then have 2 moles of your nitric. So if you just have 1 mole of calcium hydroxide, it's going to produce 1 mole of calcium nitrate. If you have 2 moles of nitric, you're producing 2 moles of calcium nitrate. Let's say you've got 2 moles of calcium hydroxide if you've got here. Wouldn't you think that could produce 2 moles of calcium nitrate? You would think, because if you got 1 mole of calcium hydroxide, it produces 1 mole of calcium nitrate. If you have 2 moles of calcium hydroxide, it produces 2 moles of calcium nitrate. But that's not the case, because in order to produce 2 moles of calcium nitrate, you would have had to have started out with 4 moles of nitric acid. And we didn't start out with 4 moles, so we can't produce it. Instead, we're introducing the concept of a limiting reagent. So the thought here is that 2 moles of calcium hydroxide could produce a total of 2 moles of calcium nitrate. But at the same time, you're only starting out with 2 moles of your nitric. 2 moles of your nitric would only produce 1 mole of your calcium nitrate. So which of these 2 is produced? Are you producing 1 mole or are you producing 2 moles? You're only going to produce the smallest number of the 2 because your nitric acid is limiting the amount of calcium nitrate that can be produced. In order for you to produce 2 moles of calcium nitrate, as could theoretically be produced by the amount you have of calcium hydroxide, you'd have to magically steal or make excess nitric. But in the problems now, I'm not letting there be excess nitric. I'm giving you an amount. And in this case, the amount was limiting. So whenever we discuss the concept of a limiting reagent, what we're asking is, how much product can we theoretically make given the amount of reactant that we have? Let me give you a real-life example. I enjoy playing soccer. So, of course, this was the first thing that kind of came to my mind was, let's say you've got a whole bunch of friends that are coming together to play soccer. In grad school, I used to play every Thursday morning, so we'd meet up at like 7 a.m., which was for grad students was super early. So we'd get there. Sometimes we'd get there even earlier, who knows. But we'd meet and show up. And sometimes we'd have like 30 people. Sometimes we'd have like 10. So on this certain day, let's say we meet and there's 12 people who show up. Soccer is typically played with 11 people on each team. So how do we proceed? We could, A, put 11 people on against one person. That'd be kind of fun. But most likely we're not going to do that. We have a couple of different options. We could either, A, have 2 teams of 6. We could have 3 teams of 4. Or we could have 4 teams of 3. So what's going to make us make up our minds? Well, one, if we're outdoors, we could easily have 2 teams of 6. But let's say we're not really feeling like running a whole lot, because to have this big, huge soccer field covered by only 6 people takes a lot of running. So let's say we have enough goals that we can shorten the field and make it so we have 4 teams of 3, then maybe we'll run a lot less, because, you know, sometimes you're just not feeling really energetic in the mornings. We could theoretically do that, have 4 teams of 3. Or if we wanted to, we could do 3 teams of 4 if we wanted to have one group kind of sub out and play the winner and that kind of thing and have a constant tournament. So what would dictate then if we're going to do 2 teams of 6 or 4 teams of 3? Okay, it's the reaction that's occurring. Do I want to be energetic? Do I want to spread out that morning? What's going on? But then also, look at the reactants that I laid out here. Not only are we limited by people, we may be limited by field space. What if there's another group of people that are using the other half of the field? Or if, say, we're working indoors, what if there's a group of, I don't know, basketball players next door or some people playing cricket? I mean, I don't know. So they may take up the other gym, so we might not be able to encompass 2 gymnasiums to spread out into 4 groups of 3. Or if, say, we only have 3 goals, we could then only play 1 game. But if we had 4 goals, we could play 2 games. So kind of what you do naturally when you come into a situation where a decision like this has to be made, you look around, you assess. Who brought the ball this morning? Did only one person bring a ball? Did 2 people bring a ball? Do you have enough to have options? If you don't have enough to be options, you're limited to only the first one, which is 2 teams of 6. But if you have enough of all the different components, you have more options and you can then choose 4 teams of 3. That is now an option. So whenever we're looking at a chemical reaction, we're doing the same thing. We're making a mental assessment of how much of each of the reactants we have to decide whether or not we have enough for each possible product. The possible products, the possible outcomes of the soccer analogy are either choosing 2 teams of 6 or 4 teams of 3. If we really wanted 4 teams of 3, we'd have to make sure we had enough reactants available to do that, which would mean we'd need 2 soccer balls, 4 nets, 2 fields, and then the same 12 people we have. Whenever you're doing a chemical reaction, it's the same process. You want to make sure you have enough of everything available in order to proceed, in order for the reaction to proceed. So let's look at this example. Our first question is, if you react 15 grams of calcium hydroxide with 5.84 grams of nitric acid, how many grams of water are produced? I kind of break this down into 2 steps. Step 1, you have to determine the limiting reagent. Are you limited because you only have 1 soccer ball? Even though you have 4 goals, it doesn't matter. You still only have 1 soccer ball. So you have to figure out what is limiting this reaction. And doing that, you want to compare the reactants in either moles or molecules. Either one will work. You cannot compare them in grams. Never, never, never. Just because you have 1 gram of something and 2 grams of something else does not mean you're limited by the 1 gram. The 1 gram may be the limiting reactant or it may be the 2 grams. The only way you can compare it is if you have it in either moles or molecules. Because if you have 1 mole of a substance and 2 moles of another substance, you know the 1 mole is limiting. If you have 5 molecules of one substance and 10 molecules of another, you know the molecules are limiting, if in fact you have the same 1-to-1 ratio. Okay? We'll look at how the ratio fits into this in a little bit. Step 2 is finish the problem, making sure to pay attention to what information is requested at the end of the problem. So finish it and make sure you're noticing what's at the end. So at the end of this problem, we're starting out with grams, and we're ending up with grams. If you report your sample in the end as moles, it's wrong. If you report it as molecules, it's wrong. So make sure you finish it out and pay attention to what's in the problem. So to begin with, this is a little bit of review from last week. We're just going to simply write down all of our molecular weights. Whenever you're converting from grams to moles, remember you need molecular weights. So anytime you start out a problem and you notice you're going to have to do a gram to mole conversion, I always just stop right there, take a break, calculate molecular weights, then come back to the problem. So this is what we figured out from last week. Calcium hydroxide had a molecular weight of 74.092 grams per mole. Nitric acid had 62.115 grams per mole. If you don't have these in front of you, go ahead and write them down now just so we can refer to them throughout the course of this lecture. Calcium nitrate has a molecular weight of 164.086 grams per mole, and then water has a molecular weight of 18.015 grams per mole. Okay, let's continue with this problem then. We got that stuff figured out. So our problem once again was if you react 1.85 grams of calcium hydroxide, 1.58, excuse me, with 5.84 grams of nitric acid, how many grams of water are produced? All right, so, and starting out this problem, we want to first do our step one, which our step one was figuring out which is limiting. So the way I always like to do this is I like to see what I'm going to get it into in the end. I'm going to produce grams of water. So what I typically do, you could work this twice and just see what comes up with the smaller number. So for instance, you could take it from 1.58 grams of calcium hydroxide and see how much water is produced, and then take 5.84 grams of nitric acid and see how much water is produced. That's all fine. I like to stop it at moles and then make that final step after the fact. But there's 100 different ways to do this. Whatever you find is a way that you feel comfortable to and that you can repeat over and over again, well, I say you do. So what I mean by that is I'm going to start out here with 1.58 grams of calcium hydroxide. I want to see how much water will be produced in moles, because you have to compare moles to moles. You can't compare grams to grams. You also cannot compare moles of one substance with moles of another. You have to compare moles to moles because you have to take into account these coefficients. If you don't take into account your coefficients, you may end up wrong. So 1.58 grams of calcium hydroxide. The first thing we want to do is convert that into moles. So we have 74.092 grams per mole. Sorry for my horrible handwriting. Grams per mole. So it's not the only thing that was bad here. 74.092 grams of calcium hydroxide per mole of calcium hydroxide. Okay. So I've got in moles of calcium hydroxide. Now what I want to do is I want to go from moles of calcium hydroxide to moles of water. Let me see how much that is. 1.58 times 2 divided by 74.092 gives me a total of 0.0426, and I'm going to keep giving it a couple more digits. We won't round quite yet. 97 moles of water. I'm keeping that in my calculator because of the fact that we're converting from grams. We want to get into grams eventually. So that's why I kept so many sig figs. So that's how many moles of water I have if I'm produced from grams of calcium hydroxide. Let's make sure my units cancel. Grams of calcium hydroxide to grams of calcium hydroxide, moles of calcium hydroxide, moles of calcium hydroxide to moles of water. Check. All right, let's then do the same thing, but with grams of nitric acid. 5.84 grams of HNO3 and for the molecular weight of that, we've got 62.115 grams of HNO3 for every 1 mole of HNO3. Then we want to convert from moles of HNO3 to moles of water. So we have 2 moles of HNO3 for every 2 moles of water. So we type that into our calculator, 5.84 divided by 62.115, and we end up with 0.094019 moles of water. So note, at that point, we've converted both of our samples into the same unit. That's what matters. If you have the same unit, both in moles and in the molecule that you're looking at, so moles of water, then you can directly compare these two numbers. So out of these two, which one is bigger? This 0.094. So whichever one is bigger, draw a big X through, and then come back all the way over, put a giant X through. Because what that means is that your nitric acid is in excess. Because it could produce a lot more than actually could be produced. So your nitric acid is the thing that's in excess. So I suggest putting a giant X through it, because I can't tell you how many times somebody starts the problem and then they figure out which one's limiting reagent, but then they use that other number for the rest of the problem, getting it wrong. So at this point, since nitric acid is in excess, that means your calcium hydroxide is your limiting reagent. And your limiting reagent is what you utilize to figure out how many grams of product are theoretically going to be produced. So that means that we can take that 0.06497 moles of water and use that to figure out how many grams of water we have. So 1 mole of water is equal to 18.015 grams of water, to give us a total of 0.04264966788 times 18.015, 0.768 grams of H2O. I check my sig figs, 3 sig figs, 3 sig figs, check. So that's what you have to do in a limiting reagent problem. It's the same as what we looked at before, with the exception that now you have 2 items that are given to you, 2 masses or 2 molar amounts of both of your reactants. And you have to figure out which one limits the true production of your sample. You figure that out by figuring out which one's limiting reagent and which one's in excess. Then you utilize the moles of your limiting reagent to calculate the grams, the mass, the moles, the molecules of your compound that you're being asked about at the end of your product. So that's our first example. Let's do another one. Here, you're asked to react 1.556 times 10 to the 23rd molecules with some number of grams to end up with grams of a product. You want to treat it the same way. So you're trying to end up with this, with comparing moles of something to moles of that same thing. And like I said, there's a bunch of ways to do that. Some people try and convert like grams of nitric into moles of calcium hydroxide. You can definitely do that. If that works for you, do it. But you're trying to compare and figure out which one's in excess and which one's limiting. So I do 1.556 times 10 to the 23rd, and this is molecules of calcium hydroxide. In order to get from molecules to moles, we need to use Avogadro's number. We now have moles of calcium hydroxide. In the end, we're trying to get to calcium nitrate. So I'm going to go ahead and convert moles of calcium hydroxide into moles of calcium nitrate. And it's at a 1-to-1 ratio. So 1.556 times 10 to the 23rd divided by 6.022 times 10 to the 23rd gives me a total of 0.258386 moles of calcium nitrate. Like I said, you could just finish that part out and go to grams if you wanted to, whichever you want to do. I want to go ahead and go back and do the other one next. 3.55 grams of HNO3. In order to go from grams to moles, you got to utilize the molecular weight, 62.115 grams of HNO3 for every 1 mole of HNO3. Then we have 2 moles of HNO3 for every 1 mole of calcium nitrate. .55 divided by 62.115 divided by 2 gives me 0.028576, and this is moles of calcium nitrate. So notice once again, I have the same units. Because I have the same unit, I can make comparisons. Which one is bigger? This number is bigger, so I cross it out and I cross this out. So this is my excess reagent. My excess reagent is our calcium hydroxide. The thing that was limiting is the one that produced the smaller number, so this is our limiting reagent. So at that point now, I can go from 0.028576 moles of calcium nitrate to grams of calcium nitrate. I could also go to molecules, but it asks for grams. So I've got calcium nitrate. The molecular weight of calcium nitrate is 164.086 grams of calcium nitrate for every 1 mole of calcium nitrate. And I end up with 4.69 grams of calcium nitrate as my final answer. So within this, there are 2 questions. It's first figuring out which is the limiting reaction, and then the reactant, and then the second part is finishing the problem. All right. So this flow chart I kind of wanted to give you. If it helps you, great, use it. If it doesn't help you, great, don't worry about it. This is the top part is what we've just looked at before. That to get from grams of an atom or a compound, you need to use the molar mass. So this right here, that's our molecular weight. And that lets you convert from grams to moles or moles to grams. Avogadro's number, that's our 6.022 times 10 to the 23rd. That lets you get from either moles of an atom or a compound to number of atoms or molecules. Back and forth, back and forth. Our balanced chemical equation, that's you get moles of a different atom or compound to moles of a different one. So you got moles of one atom or compound, and you want to get to moles of a different atom or compound. We haven't talked about this part down here much, but I kind of wanted to note that you can use the chemical formula to go from moles of an atom or compound to moles of an atom within the compound. So meaning, let's say you have 1 mole of sucrose, H12O6, I think. We'll double check that. Someone double check that. If I have 1 mole of sucrose, how many moles of carbon do I have? You have 6 moles of carbon. And so you can use that chemical formula as a ratio to go from moles of an atom or a compound. So So you would set that up as 1 mole of C6H12O6. For every mole you have of those, you have 6 moles of carbon, where you're just essentially using the subscript as the coefficient in the chemical formula conversion. Okay? And that's just kind of from the definition. So while I haven't taught on that a lot, just note that that just comes straight from the equation, the formula. All right, one last thing to talk about today. That is percent yield. This whole time we've been talking about theoretical yields. Theoretical yields is what should be produced if you create something. So meaning, if you react this 1.58 grams with 5.48 grams, the amount of water that we just calculated being produced, that answer is your theoretical yield, because that's how much in theory you should produce. But guess what? In real life, you don't actually produce that. So the way the percent yield set up is you have an actual yield over a theoretical yield. Sometimes this is called experimental yield, because that's how much you produce if you go into the lab and try and form this reaction. So the reason that you don't have theoretical yield is just because sometimes stuff doesn't go to completion. The reaction might be kinetically limited. You may spill some on the desk. You may eat some of the product. I hope not. But this is kind of what percent yield is it's allowing you to relate how much you actually got with how much you could have gotten. And so this is if you've got the CEO of the company, he would love for your actual yield to be the same as your theoretical yield. But in reality, if you're getting like 90% yields, you're doing fabulous. And yes, it depends on the reaction. So some reactions yield better percent yield, some yield worse. And so it's really all about getting that percent yield to come as close as possible. So let's do an example. Before, whenever we did this, so let's go back to that one, to that equation. So the 1.58 grams of calcium hydroxide with 5.84 grams of nitric, and how many grams of water are produced? We came up with, for our answer, 0.7628 grams of water. 0.762 grams of water. So is that your theoretical yield? Yes, because that's how much you calculated you should have produced. But what if I tell you instead you actually produced, or you went into the lab and you performed a whole bunch of reactions and you ended up calculating that you produced, and I meant to say produce there, I got distracted. You actually produced 0.579 grams of water. What is your percent yield? So what is this percent yield? That's the big question. That's the number people want to know. That's kind of one of the reasons we're doing all this math. So our percent yield equals our actual, which is 0.579 grams of water over 0.762 grams of water times 100 equals, and notice our units cancel, grams cancel with grams, and that's one thing to make sure you do, because if you have grams of one substance over grams of another, it's not going to make sense and you can't calculate the percent yield. So those units always have to be the same. So if we type that into our calculator, 0.579 divided by 0.762, we end up with, times 100, we end up with 0.7598, but then we multiply that by 100, gives us 76.0% yield. Good. What if we did this exact same problem, but I told you had a different percent yield? So 0.762 grams of water is still the theoretical yield. Okay, those are still the exact same. But what's changing is now I'm telling you that this reaction normally only has a percent yield of, let's do 51%. You But in this example we're looking at now, you did better than that. But if your company's only expecting to have 50%, how much better did you do? How much more product did you make for them than the average person used to make? Okay, so let's just do that. Let's say your percent yield is, in this example, let's just do 46.1%. So we come down here and we basically want to stick each of our numbers into the equation where they belong. So percent yield is 46.1% equals, our actual yield is 0.762 grams of water over X, where X stands for our theoretical yield, times 100. Let's rewrite this. X equals 0.762 grams of water over 46.1% times 100. Put that into our calculator. 0.762 times 100 divided by 46.1 gives us, whoopsie, let's start this slide over. Erase, erase, erase. I just accidentally drew that arrow to theoretical yield when it should have said actual yield. All right, let's do this again, but 762 grams of water, but instead we want to have a different percent yield. So we're going to be given a percent yield. So that's our theoretical yield. Our percent yield, we're going to say no, we don't want to make it that bad. Let's say it is 46.1%. So 46.1, that is our percent yield. 46.1% equals 0.7, equals X over our theoretical yield, which is 0.762 grams of water times 100. So we move all of our math over. So we've got 100 is on the bottom because it was on top over there, so it needs to be on the bottom over here. 0.762 grams of water times 46.1% equals X. So if we do that math, 0.762 times 46.1 divided by 100, then we end up with 0.351. And our units, see what units are remaining? Did this cancel with anything? No, so that has to be our units, grams of water. So in this case, we were given a percent yield and asked to calculate the actual yield. So our actual yield was 0.351 grams of water. And notice this makes sense. If you have a 50% yield, you want your actual yield to be shorter, smaller than your theoretical yield. So, kind of recap from today. When you have known amounts of two reactants, meaning one of them is in excess and one of them is limiting, you must first determine which one is the limiting reagent in order to determine the theoretical amount of the product produced. So then that theoretical part of the product produced can then be used with your percent yield equation to figure out what you may actually have made, okay? Or vice versa, where you use your actual yield to figure out your percent yield. But note, you can use all of these conversions, just as we've been doing so far, to change reactants into products. But you're really focusing on the fact that you have two amounts of reactants. To determine, you have to first figure out which one's in excess and which one's in limiting. If you have three reactants, it's the same thing. You have to figure out which one is limiting, or in that case, which one is limiting, and then you'll have two that are in excess.